we see no equivalence relation. So after that, equivalence classes. For equivalence classes, we need to find out first relation is equivalence relation or not. Then what is exactly mean by equivalence classes? Let R be an equivalence relation on set A. The set of all elements that are related to an element A of A is called the equivalence class of A. The equivalence class of A with respect to R is denoted by in square bracket A R. If B is belongs to this equivalence class A, B is called a representative of this equivalence class. Consider the example for finding the equivalence classes from the given equivalence relation. Assume R is a relation such that every order pair where A is equal to B mod 3 and it is relation on set A is equal to 0, 1, 2, 3, 4, 5, 6. So as per the condition, relation R will contain the order pairs 0, 0, 0, 3, 3, 0, 0, 6, 6, 0, 3, 3, 3, 6, 6, 3 and so on. So first element will be the A. If first element is A, then second element is B mod 3. That is the if element B, we have to choose first and A will be the B mod 3. As per that, we got all these pairs from the relation R. So pick an element 0 if A is equal to 0. In that case, equivalence class of 0 is equal to 0, 3, 6. So how this class is obtained? So this is the first element from the set A, that is 0. Equivalence class of that will be obtained by finding where the 0 is related with the to which element. 0 is related with which element. So here we can see that 0 is related with 0, 0 is related with 3 and 0 is related with 6. So this will be the equivalence classes element of 0. Then check for the element 1. Then element 1 is equal to equivalence class of element 1 will contain the element that is 1, 4. So we can see that in this relation 1 is related with 1, 1 is related with 4. That's it. So equivalence classes class of 1 will contain 1, 4. In the same way, equivalence class of 2 will contain element 2 and 5. Equivalence class of 3 will contain the element 0, then 3, then 6. That's it. So 0, 3, 6. Then equivalence class of element 4 will contain the element 1, 4, 1 and 4. Equivalence class of element 5 will contain the elements that is nothing but 2 and 5. So if you check, this is equivalence class of element 4 is equivalent to equivalence class of element 1 and equivalence class of element 5 is equivalent to equivalence class of element 2. Both contain the same element. So this is about equivalence relation on set A. Now we'll see the next concept, that is partition of the set. So a partition of set S. S is a given set. It is a collection of disjoint non-empty subset of S that have S as their union. In other words, the collection of subset AI where I is belongs to L forms a partition of S if and only if AI is not equal to phi for I is belongs to L, and AI intersection AJ is equal to phi if I is not equal to J, and union of all this subset, that is from AI A1 to AL, will gives the original set, that is nothing but S. So in short, partition of the set is nothing but we have to divide the set into different subset such that each subset is not containing any common element which is present in other subset. If you take an intersection of any two subset, it will give a phi, that is empty set, and if we union if you union all the subsets, then you will get the original set, that is nothing but S. That is called partition of the set. Consider the example for partition of the set. Let S is a set which contain element 0, 1, 2, 3, 4, 5, 6, and A1 is a partition, or we can say subset of given set. So it contains 0, 3, 6, A2 contain 1, 4, A3 contain 2, 5. So these can be treated as a partition of the set S because they not contain any common element. If you take intersection of any two subset, that is A1 A2 or A1 A3 or A2 A3, so it gives phi. And if you take a union of all these subset, that is A1 union A2 union A3, it will give the original set, that is S. So this is the partition of given set S. So we can create a different partition of the set, only the conditions will be satisfied. So more partition of the set, more ways to do the partition of set is given in these two lines. That is, we can partition like this: 0, 1, set number 1 will contain 0, 2, 4, 6, and second subset will contain 1, 3, 5. In the same way, we can do the partition like this: set number 1, that is A1 will contain 0, A2 contain 2, 11, that is 1, 2, A3 contain 3, 4, 5, and A4 contains 6. So in different ways we can do the partition of the set, only the condition should be satisfied, that is stated. Closure of the relation. We seen different types of properties of the relation, that is just what is meant by reflexive relation, what is meant by symmetric relation, what is meant by transitive relation. So now we'll see closure of the relation. For closure of the relation, we should be aware with all these properties. So what is meant by closure of relation? The closure of relation R with respect to property P, means whatever I stated, is the relation obtained by adding the minimum number of order pairs to R to obtain property P. Means we seen that reflexive relation, in case of reflexive relation, for all A which is belongs to set A pair should be exist in the relation R, then that relation is called as a reflexive relation. So if any one of the pair is missing, in that case it is a not reflexive relation. So to obtain the reflexive relation from not reflexive relation, whatever the minimum number of pair need to add into that particular relation, that is nothing but closure of that particular relation R, and it is called as a reflexive closure. So we'll see different types of closure. First one is reflexive closure. As I stated, the reflexive closure of a binary relation R on a set A is the smallest reflexive relation on A that contains R. Consider a relation R. We want to add edges to make the relation reflexive. By adding those edges, we have made a non-reflexive relation R into a reflexive relation. Here edges in the sense we can represent the relation in the form of digraph, and digraph contain the nodes, that nodes and edges. So nodes is nothing but the that elements from the set A, and edges is nothing but the how the elements are related with the other elements. So you aware with how to represent relation in the form diagram. So considering that diagram, this statement is stated, we want to add edges to make the relation reflexive. By adding those edges, we have made a non-reflexive relation R into a reflexive relation. That is called as a reflexive closure. Consider the example. Relation R is given, which contain the pair 1, 1, 2, 2, 1, 2. These three order pairs in the relation. It is not and it is on set A, which containing the element 1, 2, 3. So if you see, reflexive property is not satisfied by the relation, as 3, 3 pair is not present in the relation. So here R is not reflexive. To make it reflexive, we need to add 3, 3 order pair into the relation. So this new relation, after adding this 3, 3, is called as a reflexive closure of R. That is 1, 1, 2, 2, 3, 3, 1, 2. So for making the relation reflexive, if you see, it contains original R in it. So that is 1, 1, 2, 2 and 1, 2. So in reflexive closure, if you say that reflexive closure is equal to R union whatever the pairs required, extra pair required, that is 3, 3, and then it is called as reflexive closure. And one more condition, that it should be minimum, that is minimum, or we can say smallest reflexive relation, because we can add extra pair in it, but we not added. So we can add here 1, 3, 1, 2, 1, 2 is there, so 2, 1, but that pair is not added because it's not required. So minimal, or we can say smallest reflexive relation, which satisfying the property of reflexive, then it is called as a reflexive closure of the given relation R. The same way, symmetric closure, here the property is only the symmetric property should be satisfied. So the symmetric closure of a binary relation R on set A is the smallest symmetric relation on A that contains R. Consider a relation R which is represented in diagram. So we want to add edges to make the relation symmetric. By adding those edges, we have made a non-symmetric relation R into a symmetric relation. We seen that in case of symmetric property, if A, B pair is belongs to relation R, then B, A pair should be belongs to R. It is for all A, B belongs to set A. So consider the example. This relation is given. R is equal to 1, 1, 2, 2 pair is there, 1, 2 pair is there. So on set A, 1, 2, 3. Here R is not symmetric because 1, 2 is belongs to R, but 2, 1 is not belongs to R. So it is not symmetric. To make it symmetric, we need to add 2, 1 order pair into relation R. So after adding 2, 1, this new relation is called symmetric closure of R. So in the same here also extra pairs are not added, only the essential pair which make the relation symmetric is added. That's why it is called as smallest symmetric relation, and that is nothing but symmetric closure of given relation R. Then last one is transitive closure. Transitive, in case of transitive property, we know that if A, B pair order pair is belongs to relation R and B, C is also belongs to R, then A, C should be present in relation R. So in mathematics, transitive closure of a binary relation R on a set A is the smallest relation on A that contains R and is transitive. So let A is a set which containing element 1, 2, 3, 4, and let R is a relation on set A which contain pair 1, 2, 2, 3, 3, 4, and 2, 1. So to finding the transitive closure of that, we have to check all the pairs like 1, 2, 2, 3. So 1, 3 should be present